Hello and welcome to our first Higher Chemistry online revision session. My name is Dr Maureen Monaghan. I'll be leading the sessions along with my colleague Mr Paul McCrainer. Between us we have nearly 30 years experience of teaching chemistry. We have both worked with the SQA as markers, and Mr McCrainer is one of the authors of the Hodder-Gibson Nat 5 chemistry textbook. So let's get started on our first session. By the end of this session, you should be able to describe how ionic and covalent bonds arise, understand the concept of the bonding continuum, which is a spectrum of bonding which stretches from ionic bonds through to pure covalent bonds. You should be able to identify a polar covalent bond and use delta positive and delta negative to show partial charges on atoms making these polar bonds. The type of bond an atom will make with another atom really depends on the electronegativity, the attraction an atom has for the electrons in a bond. I'm just going over the trends in electronegativity. If we're going across the period from lithium to fluorine, we have same shielding. We popped in our electron arrangement there for lithium. We've got 2, 1. Fluorine, we've got 2, 7. The shielding effect or the screening effect due to the inner shell electrons is the same for both of these elements. They both have one full inner shell. That inner shell is full for both of them. So the shielding of the nucleus is the same. The difference though is that lithium only has 3 protons, whereas fluorine has 9 protons. So there's a stronger pull from the nucleus for fluorine, which means its own electrons are held more tightly, but it also means that it's very good at pulling electrons from another element as well. It's very good at attracting the electrons in a bond. As we go down a group, using lithium and potassium as an example, the number of electron shells are increasing. That means the nucleus is further away from the electrons in the bond, and so it's not going to be as good at attracting those electrons. So it's a weaker attraction for the electrons in the bond compared to the likes of lithium, only has 2 shells, so the nucleus has a stronger attraction, the atom has a stronger attraction for the electrons in the bond. The different types of bonding then arise when the atoms have a different electronegativity from each other. So 3 scenarios we could have when comparing electronegativity of 2 different atoms that are bonding. We could have a really big difference in electronegativity which will result in an ionic bond, a small difference which can result in a polar covalent bond, or when there's no difference at all, and that's what we would call a pure covalent bond. We're just going to take a moment to look at each of these in turn. So an ionic compound that we are all familiar with is sodium chloride. We can go to page 11 in your data booklet and look up the electronegativity values of these elements. We find that sodium has an electronegativity of 0.9, chlorine 3.0, and that gives us an electronegativity difference of 2.1, which is quite big. When we look at our electron arrangement, sodium is 281, chlorine is 287. Chlorine has a much greater attraction for the electrons in sodium, so much so that it pinches the outer electron, the valence electron of sodium, and takes it for itself. These interactions can be viewed almost like a tug of war, and we find that sodium then will have an electron arrangement of 2,8, chlorine 2,8,8, and that has given us charges on those ions. We have a sodium ion, we have a chloride ion. The electron has transferred, and it's transferred because the difference in electronegativity was so great. Chlorine had a much stronger attraction for the electrons in the bond than sodium, so it just took it completely. It won the tug of war outright. At the other end of the spectrum we have the situation where there is no difference in electronegativity between the two atoms that are bonding. These little dots here are trying to represent the electrons that are shared between the two atoms making the bond, and here they are shared equally, they're right in the middle. Again, looking at our tug of war analogy, neither element is stronger than the other. They both have the same attraction, the same pulling power, and so the electrons are shared absolutely equally between them. This would happen when an element is bonding with itself, example hydrogen bonding with itself, or there are some elements like carbon and sulfur where they have absolutely the same electronegativity, the same attraction for those electrons, and if we're showing the position of the electrons with these wee dots, the electrons will be right in the middle, shared equally between the two elements. Finally, we have this polar covalent bond, and that's when the difference in electronegativity isn't big enough for one element, one atom, to get the electrons entirely. But the electrons will be shared unequally. They'll be closer to one of the atoms in the bond, and that results in partial charges. This one is a little bit negative, this one is a little bit positive, and this is the Greek symbol delta, so we say delta positive, delta negative. An example for that would be oxygen bonding with hydrogen. If we look up their electronegativity values, we have 3.5 for oxygen and only 2.2 for hydrogen. So we have a difference of 1.3 in the electronegativity values there, and in this circumstance it's not enough for oxygen with the higher electronegativity to get the electrons entirely, but those electrons will definitely be closer to oxygen, and so we can give the oxygen this partial charge, a little bit negative, and hydrogen's delta positive, a little bit positive. So a partial charge, not a full charge. And when we have this difference in charges across a bond, we say there is a dipole. So di meaning two poles, there's two poles of this bond, a slightly negative pole and a slightly positive pole, dipoles. Hydrogen chloride would be another example. Hydrogen, again, electronegativity of 2.2. I'm just getting these values from page 11 in your data booklet. Chlorine 3.0, given as a difference of 0.8. So not as big a difference as the last time, but still considered polar. Still a polar bond. So electrons are going to be closer to the chlorine, giving the chlorine a partial negative charge, hydrogen a partial positive charge. Delta negative for chlorine, delta positive for hydrogen. So the electrons are shared unequally, and we have a dipole across this bond, a charge difference across the bond. So we've looked at those three bonding types, but the fact is there is no strict cut-off point between them. We would talk about a bond being of more ionic character than another one, or being more polar or less polar. We don't have a strict cut-off point, and this leads us to the bonding continuum. It really is a spectrum playing on the difference of electronegativities, and there's a gradual change as we go across. And here we are going across a period, looking at different elements of the period bonding with fluorine, and you can see we've got gradual changes here. Aluminium fluoride is still ionic. Silicon tetrafluoride is a covalent molecule. Now, how do we know for sure? We've got to look at properties. You should know well by now that ionic, we've got a high melting and boiling point, and it conducts when liquid. Our molecules have lower melting and boiling points, and they do not conduct electricity. So we're able to tell them apart by their properties. A good example to remind us of the importance of looking at properties are two hydrogen compounds. Sodium hydride, look at the electronegativity difference between sodium and hydrogen is 1.3, but sodium hydride is ionic. compared to hydrogen fluoride, where we've got an electronegativity difference of 1.8, that is polar covalent bonding there. We have to look at the properties. How do we know which is which? Ionic, high melting and boiling point, will conduct as a liquid. Covalent, low melting and boiling points when we're talking about covalent molecules, of course. And there is no conduction of electricity. We must look at the properties. At the pure covalent side, for it to be considered absolutely pure covalent bond, there should be no difference whatsoever in the electronegativity. In practice, when we have elements bonding where the difference in electronegativity is 0.4, 0.3, that's really not significant. Strictly speaking though, the bond is still slightly polar. So a few examples now of showing the partial charges and how to assign them to the atoms in the bond. Let's start with nitrogen with fluorine. If we look up the values for the electronegativity, nitrogen is 3.0, fluorine is 4.0. Fluorine has the higher electronegativity, it's going to have the greater attraction for the electrons in the bond. So let's get these in. I'm using the delta sign, and it's like a number 8 that you've not quite finished off. So delta negative for the fluorine and delta positive for the nitrogen. This time I'll compare nitrogen with hydrogen, and again looking up those electronegativity values, we have our 3.0 for nitrogen, 2.2 for hydrogen, and the one with the highest electronegativity is the one that is better at attracting the electrons in a bond. So the electrons will be slightly closer to nitrogen than to hydrogen. That gives it a partial charge, delta negative, whereas the hydrogen is just a little bit positive, and that's showing the dipole across that bond. A very polar bond, oxygen bonding with hydrogen, and electronegativity values this time 3.5 for the oxygen, 2.2 for our hydrogen. Oxygen is the highest electronegativity, so it's going to be a little bit negative. Hydrogen a little bit positive. Now you'll have noticed in these examples that I haven't shown the electrons in the bond. In day to day we don't generally put that in, but it will come up in past paper questions, and if you watch our other video that is showing some examples of past paper questions in this topic, you will see an example of that there. SQA does expect you to understand that the electrons are closer to the atom that has a higher electronegativity. We've looked at how to assign the partial charges when we have just two atoms paired together, but what happens in the situation where you have molecules? Let's look at something like ethanol, and we can just fill in round about the electronegativity values of the different atoms that are there. At a higher level, we look at the most significant polar bond in a molecule. We can look at the different polarities and say, okay, between hydrogen and carbon there's a 0.3 difference, but that's not overly significant, not compared to the difference of 1.3 that we have between oxygen and hydrogen. The difference between the carbon and oxygen is also significant, and we could assign that as a polar bond as well and add our partial charges too. So in this situation, carbon would be a little bit positive, oxygen's a bit negative, and the hydrogen's a little bit positive. We won't bother with the carbon and hydrogens because compared to the other two polar bonds in this molecule, they aren't significant. If you're trying to decide if a molecule has polar bonds and you're trying to do this very quickly, the key ones to look out for is oxygen bonded to hydrogen, nitrogen bonded to hydrogen. These are really important key bonds that show there is a polar bond there, and if you spot that in a molecule, that's your polar bond to go for. So hopefully you now understand how we get our ionic and covalent bonds. It's all down to the difference in electronegativity, and they are at opposite ends of a spectrum of a bonding continuum. There are gradual changes as we go across. You should be able to identify a polar covalent bond in a molecule, and you should be able to use the delta positive, delta negative to show partial charges on atoms. You now have questions to try on this before the webinar, and in the webinar you will have a chance to ask for help if you're not understanding something. It would be really useful if you would fill in the forms so we can identify if there's parts that aren't clear or things you need extra help with. That would be really useful for us to have that information before the webinar so it can be as useful as possible for you.